Hello, this is Mr. Huebner, and we are working on the bonding notes, Unit 3, and apparently it's Part 3. Okay, so hybridization, that's the focus. All right, so here's some review. We kind of did the memorization of hybridization, SP3, SP2, SP, and then you got the SP3D and the SP3D2. And I said just memorize it. And we'll talk about it later. Well, here's the time we're talking about it later. So just to review, linear is going to be a SP hybridization. Trigonal, planar, and bent are going to be SP2. And this is providing it's a one lone pair type of bent. Because if it's a, let's see. Yeah, if it's a two lone pair, then it's SP3, which, okay, that's right. Yeah, so the one lone pair bent, and then the two lone pair bent, SP3. Trigonal pyramidal, tetrahedral. So these are all the basic ones that we talk about in sophomore level chemistry, but we put our big boy pants on in IB, and we learn all of the exceptions to the octet. We got SP3D. And what causes these exceptions, this ability to break the octet rule? It's the presence of the d orbital, and you have empty spots available for these extra electrons to be put into. You got trigonal pyramidal, seesaw, T-shape, linear, and basically if you count all of the lone pairs on the center atom, including the terminal atoms connected, and it's 5. Because you got 1s, 3 p's, and 1d, add them up, that's 5. You know it's sp3d. And then maxing it out is sp3d2. When looking at hybridization and explaining the theory behind it, we're focusing on sp, sp2, sp3. sp3d, sp3d2 is theory that's on shaky ground, and some literature is contesting it. So we're like, okay, we'll just focus on these because that's not really contested or disputed. All right. Moving on, a summary of the localized electron model. So LE model. This is looking at basically what we've been doing. You got the bent shape, you got the tetrahedral shape, and these different structures because you got the sharing of the electrons. Term the hybrid atomic orbitals. Alright, so the problems with this model, though, are numerous in that it does not explain resonance structures or the bond angles associated with the different shapes. So if you have, for example, tetrahedral, like, how do we know it's less than 109.5? It should be, shouldn't it be like a 90-degree angle? Why is it 109.5? And the explanation is hybridization causes it to be at that specific bond angle. So the idea of hybridization kind of explains the things that can't be really explained in just the molecular dot structure theory and idea, localized electron model. Oh, I pretty much just summarized that. Okay. Yeah, just reading it says, for example, the carbon atom in a molecule of methane is experimentally found to have 4 identical in energy CH bonds in the tetrahedral shape with a bond angle of 109.5 degrees. This, though, doesn't make sense if we simply think of atomic orbital overlapping, because carbon would have 2 valence electrons in s orbitals and another 2 in p orbitals. So let's just write that out. Carbon is 1s2, 2s2. Oh my gosh, I don't have a paper periodic table on me. Just double check this. Don't look at that. That's my winter break task. Okay. Pretty sure what, there's 6 electrons in carbon? Just want to make sure. Yeah, 6. Okay. So it's 1s2, 2s2, 2p2. All right, so that's the electron configuration. So what are they saying? This doesn't make sense if we simply think of atomic orbital overlapping, because carbon would have 2 valence electrons in s orbitals and another 2 in p orbitals. There it is. Here's our valence. They have 4 outer electrons, carbon. We just thought of the electrons being in overlapping atomic orbitals, then the p orbitals should be at 90 degree angles to one another. A modification is necessary in which the s and p orbitals are thought of as coming together as hybrids. This is called hybridization. So, like, this looks very much like 90, but they do a bunch of sophisticated experiments that are beyond this course. Don't have to worry about it. They found that it's 109.5, and so hybridization theory is there to explain that. All right. What we got? CH4 and sp3 hybridization. So, in your book, they've got a nice little visual that has paint. Paint is something I can understand. I like painting. And they got red paint and white paint buckets. But then, when you mix them, red and white make pink. So there you go. So basically, hybridized orbitals are mixtures of the 2 orbitals. And when we're talking about sp3, we're talking about the mixing of the s orbital, which is a spherical shape, and the p orbital, which is the bow tie shape. So you can see it. We got the spherical s and the bow tie p. And there's 3 of these p's. And they're all mixing to form one thing. And if we're using, they use box to describe this, but usually IB uses for the orbital filling diagram circles. But here they went off boxes. Usually AP Chem is with boxes. I actually prefer boxes, but let's see. So as we got energy, so here's the 1s, and then we got the 2s, and then there's the 2p. S is represented by 1 circle or 1 box, and p is represented by 3 circles or 3 boxes. All right. If you take chemistry in America in college, you're going to be seeing the boxes, not the circles. All right, and we're talking about carbon. It's got 1, 2, 3, 4, 5, 6. So that's kind of like the orbital. Sorry, let's get this in here so you can see it. There it is. Here's the orbital filling diagram of regular carbon. But when we start to apply the hybridization idea, let's rewrite this. We got 1s, 2s, and 2p. 1 box, 1 box, 3 boxes. What happens is one of these electrons in the s is going to float over here, and they're going to mesh together in one hybridized orbital. So all of these are considered sp3 because you got 1s and 3p suborbitals. So it's sp3 hybridized. Oh man, and I took all my space to make my pretty picture, so I apologize for that. I'm going to have to squeeze it in over there probably. Okay. So here's just kind of what it looks like if we're representing them with boxes. Because really we're trying to represent something that we cannot see. So we got the SPPP for sp3 hybridized orbitals. All right, and then the picture, if we're doing CH4, I'm going to put C in the center, and we got H's, 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 H's. Here we got sp3 hybridized, sp3, sp3. All right, so essentially what you have is you've got an overlap of the 2p orbital of carbon. Where is it? The 2p. with the 1s orbital of hydrogen. So you got that happening in there. And then you also have the 2s of the carbon interacting with the 2s of the hydrogen. So you have kind of two of those situations happening. So like this is, yeah, hydrogen, all it has is the 1s orbital, 1s1, and that's going to be merging with the 2p. And then you have also the 2s of the carbon merging with the 2s. So essentially, you have two different types of sp3 hybridized bonds. And that's what's causing it to not be a 90-degree angle. It's kind of twisting it because now you have a meshing of orbitals. So, because that's kind of the theory behind it. And we got 1, 2, 3, 4 sp3 hybridized bonds. All right. You're also going to have in CH4, let's just draw it out without the clutter. Oh my gosh. You got 1, 2, 3, 4 bonds happening, and every single bond is going to have a sigma bond. Oh, there it is right there. Yeah, sigma bond. And let's see. It's basically a head-on collision between the s orbitals. So let's see what the definition, technical definition, it says a covalent bond in which the electron pair is shared in an area centered on a line running between the atoms. This is essentially direct overlap of any type of orbitals, hybrid or unhybridized. Every time there's a single bond, this is a sigma bond. So that's the main idea that you'll need to know to answer questions correctly on the test or IB exam. Every time you got a single bond, you have one sigma bond, and it's essentially an overlap between two orbitals, whether they're unhybridized or hybridized. So a simple picture would be, I don't know, here we got, and right there is the sigma bond. It's a direct overlap meshing of orbitals in the sharing of these electrons. All right, it's the Greek symbol sigma. Moving on. Oh my gosh, we got till 35. Okay. Whew, let's try to get through. Okay, yeah, we just got to get through these two things, and then we're done. All right. So, I'm going to go with the example in the book, and I believe it was C2H2. What did I have? No, C2H4. Yeah, C2H2 over here. All right. So let's do the orbital filling diagram picture again. We've got, I got to squeeze it in a little smaller. We got 2s and 2p. I'm just writing the 2s and the 2p because that's what's involved in the bonding here, not the 1s. And we're talking about, well, this is what it normally looks like, carbon. You got, the 1s, 2, 3, 4, 5, 6. But just like what happened over here, we're going to have a moving and a hybridization. So, one of these electrons is going to pop up over here. However, in this situation, you're only going to have two of the p suborbitals undergo hybridization, and one's going to be kind of doing its own thing. All right, so these are sp2 hybridized. And if we rewrite it, it's going to be 1, 2, 3. We got 3 sp2 hybrid orbitals. And here we just have one unhybridized p orbital. So when we're making our little shape, we've got carbon and carbon. We got sp2, sp2. We got two p orbitals meshing with one s orbital. We got H. We got H. Here's an sp2. An sp2, and we got the same thing happening here. sp2, an H atom, sp2, and an H atom. We now have to put our unhybridized orbital there, and this is kind of floating right here. This is our P, unhybridized, not meshing. And right here we got a sigma bond, we got a direct overlap. Every single bond you have between carbon-hydrogen and carbon-carbon, you have one sigma bond, so we're going to have like 1, 2, 3, 4, 5 total sigma bonds happening. But then we also have what's called a pi bond, represented by symbol pi. And a pi bond is the parallel attraction between two unhybridized orbitals. And it creates a more stable bond. Now in the sp3 hybridization, it's only going to be single bonds, only single. But when you have sp2, you're going to have one double bond present. So this is a double bond, and if we write it out, that's what it's going to look like. 1, 2, 3, 4, 5 sigma, 1 pi bond. 2, 4, 6, 8, we got them. Alright, so that's sp2 hybridized. We got just enough time to, well, let's talk about pi bond and then sp hybridization. So pi bond, a covalent bond in which parallel, unhybridized, right there, p orbitals share an electron pair occupying the space above and below the line joining the atoms. This is indirect overlap of p orbitals. In a double bond, there is one sigma bond and one pi bond. In a triple bond, there is one sigma and two pi bonds, which we're going to get right here in the sp hybridization. All right. So, doing the little orbital filling diagram, we got 2s. We're still dealing with carbon. We've got 2p. So normally you have 2 electrons in here. And then 2 electrons in the p, but one moves over and hybridization occurs. So, but the hybridization that occurs here is just 1s and 1p. So then what we're going to do is we're going to move into what it looks like hybridized. This is 2 sp hybrid orbitals, and then you have 2 that are unhybridized. Two unhybridized p orbitals. Alright. So then drawing the picture, just as it said here, 1 sigma bond and 2 pi bonds, it gets a little in need of artistic skills, which unfortunately I lack. We got sp, a direct collision, that's our 1 sigma, and then it's, let's just write this out. We're going to need a triple bond in there, 2, 4, 6, 8. So there's our sp. Again, we got 2 sp hybrid orbitals, 1, 2. This one has 1, 2. And then we have 2 unhybridized p orbitals. Alright, here's my best shot. Here's our 1 unhybridized p orbital. P, 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 and we've got our pi bond, and then our other pi bond. So we got our 1 sigma bond and our 1, 2 pi bonds occurring. So if we're continuing on with this, we've got only single bonds. Here we got 1 double bond, and here we're going to have 1 triple. But could you have a situation where you have 2 double? Yeah, or 2 double. Like in the case of CO2, you're going to have this sp hybridization, but that you don't have a triple bond, you have a double and a double on both sides. All right. And that is hybridization. I think we'll call it quits on that. I'll put a pause on the video. See you guys later, video. All right.